Welcome to section 10.3 Logarithmic Functions. Okay, so the logarithm, which is on page 668, the definition is for all positive numbers, a, where a is not equal to 1, and all positive real numbers, x, what do we have? Y equals log, and we say log base a of x is equivalent to x equals a to the y power. So we found a way to connect the exponential equations to something we call a logarithmic equation. And basically, it's sort of the inverse of the exponential when you switch the x and the y values. So it's a new form of a function or a new form of an equation we're looking at. So once again, how we read this is log, and then you write base and x. Now, the x value here is called the argument, and that should be on the same line as the log. If you're writing on lined paper, it'd be on the same line. And then the a is a subscript, so it should be down by the tail of the g. And that is called, once again, the base. Alright, so what is the meaning of log base a of x? Well, the logarithm is an exponent, so a log is an exponent. The expression log base a of x represents the exponent to which, getting some fancy wording here, to which the base a must be raised to get x, or to obtain x. So if we take a look back at what we saw earlier, a to what exponent gives me x? So basically the answer is y is equal to this value here. That's sort of the way we describe the exponent. A little confusing, sometimes it takes a little bit of time, so just slowly work through the problems. And once again, if you have questions on any of these, please come by the office hours or send me an email. I'll be glad to help. Okay, example 1. Convert between exponential form to logarithmic form for the following. Alright, so once again, logarithmic and exponential are interchangeable, or they're tied together. So what do we know? Well, the exponent is going to be our y value. So let me go ahead and color code this to what I had. So that's my exponent, the y. And then the answer was my x value. And the base is 3. So one thing you'll note is the base stays the same between the exponent and the logarithm. Okay, so this is going to end up being log base 3. Once again, the base stays the same. Log base 3 of 9 equals 2. And that's how we translate it. So what you can think of it, the log is saying 3 raised to what power would give me 9? And I say, well, 3 raised to the second power would give me 9. Okay, so log is sort of stating a question, if you want to think of it that way. So let's take a look at the next one. b 1/5 negative 2 equals 25. So we can go ahead and say log base 1/5 raised to what exponent would give me 25? And the answer is raised to the negative 2 exponent. Let's go ahead and do the other one. So log base what? Well, once again, the base is always going to stay the same between exponent and log. So log base 4 of what exponent would give me 1 and 64? Well, that would be the negative 3rd power. There are definitely different ways to look at this, so if you need different ways to look at it, please send me an email or drop by the office hour. Alright, example 2. Solve the following logarithmic equations. Okay, so one thing to note, how do I know this is a logarithmic equation? As I stated before in other videos, you really want to know what kind of an equation you're looking at, because that gives you the sort of battle plan on how to get there. Okay, so how do I know this is a logarithmic equation? I said that wrong. How do I know this is a logarithmic equation? Well, the word log is in all of them. So it's a pretty good sign. It's a logarithmic equation. And then the question is, where is my variable? So let's take a look at A first. Where's my variable? Well, it's inside the argument. Now, you can't touch the argument. So how do I get it outside of the argument? Well, my plan is, the only thing I really know how to do right now is to convert from logarithmic form to exponential form. So since logarithmic form is not helping me, let's change to exponential form and see if that helps. Well, remember the base is always the same, so this is going to be 4. And the answer is the exponent, so that's 4 to the negative 2 power equals x. Alright, so I changed to exponential, and what do you know? I've already solved for x. That was so easy. Now all I have to do is simplify that negative 2. So that would be 1 over 4 to the second power equals x, which I can once again simplify. 1 over 16 equals x. That was pretty easy. So it's a great trick to remember when you're working. If you're solving with logarithmic, if you have x in the argument, sometimes it's good to try and switch to exponential form. Great plan. So let's take a look at the next one. Once again, the variable is inside the argument. So in order to solve for it, I need to get it out of the argument. So let's go ahead and switch to exponential form. Now another way I like to practice switching to exponential is I follow some arrows. I say the base raised to this power gives me that. I follow a circular pattern. So 1/3 raised to the second power equals 2x plus 5. And what do you know? This is like a linear equation. We know how to solve these. So 1/3 to the second power is going to be 1/9 equals 2x plus 5. Let's go ahead and subtract 5 from both sides. Building up property, 9 times 9. That's going to be negative 45 plus 1 over 9 equals 2x. And that'll be negative 44 over 9 equals 2x. And then getting x by itself, last thing to do, divide by 2, or multiply by half. It's the same thing. And that will be, let's go ahead and simplify the 2 and the 44. So that will be 22. So that'll be negative 22 over 9 equals x. And let's take a look at the last one. Ooh, this is different. How is it different? Well, my variable this time is appearing in the base, not in the argument. But same thing, I can't work with it right now how it is, so I have to go ahead and switch to exponential form. So the base raised to that equals that. So x raised to the 4th power equals 5. Do we know how to solve this? Yeah, we do. Let's go ahead and take the 4th root, and when we take the 4th root, we have to be careful and include the plus or minuses. That's whenever you're taking an even root. You have to remember to do the plus or minus. That cancels, and x is equal to plus or minus the 4th root of 5. However, if you recall the base, what do we know at the base? The x value needs to be positive numbers. All positive real numbers. So, we're not allowed to have that negative for x. So x equals positive 4 root 5 because x needs to be positive. Once again, if you ever cross out one of the answers or you ever discard it, you need to state the reason why you're discarding it. So this is the reason why we discarded the negative, because the x value, or the base, needs to be positive. So let's take a look at some of the special properties, which is on page 671. So for any positive real number, b, where b is not equal to 1, the following is true. Sorry for the messy handwriting. Okay, so log base b of b equals, well, what do you think? This is asking us, b raised to what power would give me b? What power do you need to raise b to get b? Well, it's just 1, right? B to the first power would give me back b. Okay. And then log base b of b to the r. Well, using the same concept, this is saying b raised to what power would give me b to the r? Right? B raised to what power would give me b to the r? Well, r, right? So that'll equal r. And 2 more. So, log base b. Log base b of 1 equals what? Now this is saying b raised to what power would give me 1? Let's write that out. B to what power equals 1? Well, there's only one way to get 1 as the answer, and that is raising it to the 0 power. So anything where the argument is 1, the answer is 0. And last one. B of log base b of r equals r. Now, one thing to really note, if handwriting is not always the neatest, which is something that I struggle with sometimes, you want to be really careful with working with logarithms. And this is something I do grade on the exam. Your bases need to be down by the tail of the log, and your argument needs to be with the main part of the log. And then any exponents on the argument need to be above the log. So there are 4 things you got to watch out for. The bases, and then, 3 things. The bases, the exponents on your argument, and your argument. Okay, got to watch out for those. So make sure the subscripts and everything are in the right place. All right, let's take a look at evaluating the following logarithms. So log base 7 of 7. Well, this is saying 7 raised to what power gives me 7? Or we could just use the cancellation rule we have above. We know they cancel out, and our answer is 1. That was short and simple. The next one, the base matches the argument. Using the cancellation rule, right here, we can go ahead and cancel those, and we're left with the answer of 6. Next one. Ooh, which one does this match? Well, the base and the argument aren't the same. However, the argument is a 1, which is this one right here. That answer is 0. Anything with an argument of 1 is 0. Now the next one. Wow, that looks complicated. But notice, this matches the base. That works with this one right here. We can cancel those out, and we're just left with the argument, which is 13. And last but not least, ooh, this one's a little complicated. It doesn't match any of mine right now because the bases don't match. However, I see a 3 and a 3, so I'm going to be tricky. I'm going to be clever here. Can I rewrite 1/3 as 3? Well, I know 1/3 is the same as 3 to the negative 1 power. So I can rewrite this as log base 3 of 3 to the negative 1. And what do you know? The bases match the argument, so they cancel out, and I'm left with negative 1. So, once again, I don't know if you'll notice, but especially moving forward, the rule for the negative exponent, the reciprocal rule, is very useful to remember. Okay, so whenever you're working with something and you see that, make sure you just think about that if you ever see a negative exponent. It's always a good trick to have up your sleeve. Okay, so let's take a look at the next thing, logarithmic function. So page 672, what do we know? Well, if x and a, so let me go ahead and say, if a and x are positive real numbers, and a does not equal 1, then what do we know? Then g of x equals log base a of x. So this is a logarithmic function. And how do we know it's a function? Because it states g of x. Alright, so let's go ahead and graph this function. Log base 6 of x. Well, whenever we graph things, we want to have at least 3 points, and always try to find the intercepts if possible. And as usual, I like to pick 0 as one of the input values, and then a positive and a negative. So let's go ahead and pick 0 first. Well, that's going to be log base 6 of 0. So this is saying 6 raised to what power? 6 raised to what power would give me 0? Well, let's pick a positive number. 6 to like the second power. No, that would be 36. Any positive number would give me a big number. So I know positive numbers don't work. And let's see. Let's try 0. We have positive, 0, and negative numbers. Those are the only ones that exist. We know positive didn't work. If I try 0, 6 to the 0 power, what do I get? Darn, 6 to the 0 power is going to give me 1. So that doesn't work either. One last attempt to try to see if we can find something that makes it equal to 0. Let's see. Picking a negative number, how about negative 1? Well, that's going to give me 1 over 6, which is not equal to 0. In fact, any negative number is just going to give me a reciprocal of 6 to that number. I'm never going to get 0. So it's impossible. There is no way to raise 6 to a power and get 0. So my answer doesn't exist. And notice this would be the y-intercept. So the y-intercept does not exist. Interesting. Let's go ahead and pick another value. Let's go ahead with, well, you know what? One of the hard things here is when I'm working with it this way, y equals log base 6 of x. If I'm picking values for the argument, picking these values, I have to spend time thinking about how I would raise 6 to get those values. It's not really hard, but it just makes it a little more complicated. So let's just think of something. Recall that x is the answer, also known as the argument. Notice they both have a's. And y is the exponent. So I'm going to think a little backwards here. What's a power I can raise 6 to? Well, let's say positive 2, right? If I raise 6 to the second power, what's my answer? That's going to be 36. So when I raise 6 to the second power, I get 36. And let's pick another one. How about, well, we always want, negatives. Well, let's go ahead and do that. So 6 to the negative 1, 6 to the negative 1, that's going to be 1 over 6, right? 1 over 6. Okay, so we have we only have 2 points. We need another point. Well, we haven't done 0 for y. Why not? Let's do that. So 6 to the 0 power is going to give me, well, 6 to the 0 is 1. All right, so now we have 3 points, and we managed to find the x-intercept, 0, 1. And there was no y-intercept. So let's go ahead and graph this. My y values, my x values. Okay, what do we have here? We have 36 and 2. That's kind of large. I'm going to back down a little bit. How about we pick 1 for y? So when we raise 6 to the first power, we get 6. So let's go ahead and work with these 3, graphing those. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay, so we have the point 6, 1. Up 6 over 1. 6, 1. And then we have the point 1/6 negative 1. So let's see, 1/6 negative 1 down here. And then we have the point 1, 0. 1, 0 right here. And that's basically it. It'd be really hard to graph this point, which is once again why I picked this point right here. Okay, so let's go ahead and fill those in. And one quick thing to note. Does my graph cross the y-axis? It doesn't, because if you recall, we do not have a y-intercept, which means there's actually a horizontal asymptote right here at x equals 0. So my graph, when I graph it, can approach, but it does not actually touch. And there we go, the logarithmic graph. A little tricky sometimes because you're working with the opposite of an exponent, but once again, just take some time, mull it over, and once again, if you have questions, just let me know. Alright, so what are some of the characteristics of the graph? Well, one of the first characteristics we have is it contains the point 1, 0, which is the x-intercept. And we saw that right here. There's our x-intercept right there. What else do we know? Well, the function is 1 to 1, which means for each x there is one y. So it's 1 to 1. And let's see. When a is greater than 1, it rises from left to right, like this. And then when a is less than 1, what do we know? Or not just less than 1, sorry, it needs to be in between 0 and 1. 0 less than or equal to a, less than or equal to 1. It's going to be falling from left to right. So it'll look kind of like this. Once again, these are just very basic sketches. And a third thing to know. So the y-axis is an asymptote. To be more specific, it is a vertical asymptote. Okay, so it'll approach it, but it'll never touch it. And that's what we saw when we noticed we didn't have a y-intercept, because we have that horizontal asymptote, or sorry, that vertical asymptote right there. And one other thing that's a characteristic of the graph. The domain is 0 to infinity. Notice it's not including 0. And the range is negative infinity to infinity. So let's take a look at that. Domain, the x values, are from 0 to infinity, but we don't include 0. And then our range is from negative infinity all the way to positive infinity. So one thing you'll note is that the logarithmic graph and the exponential graph are very similar. They're just basically reverses of each other. Okay, and that is it for this section. Once again, if you have any questions, please send me an email or come by an office hour.